Now we are going to discuss the effect of temperature on the equilibrium constant. Remember that the equilibrium constant was defined as the standard Gibbs free energy change at constant some defined pressure, which was 1 bar. So it means that the equilibrium constant will now change with respect to temperature, because there was no specification with respect to temperature. So we can actually define the equilibrium constant in different, there are different ways of thinking about how the equilibrium constant is changing with respect to temperature, but would like to connect it to the heat or the enthalpy of the reaction, because usually you see you try to follow the heat released in the reaction, in the chemical reaction, but here we are talking about the delta G, not the delta H, but the question is how will you connect it, and that connection was meant by Van 't Hoff, and Van 't Hoff did a lot of work on thermodynamics as well as chemical kinetics, and he studied many different systems, and he was the first to receive the Nobel Prize in chemistry, and also he and Oswald together started the first journal or basically periodical on physical chemistry. Around 1887 they started together this beautiful journal called Zaitsev of Physical Chemistry. You can actually read about it more on some web resource. Now we're just going to discuss the Van 't Hoff treatment, how the equilibrium constant is going to affect the temperature. Now what we are going to do is already known to you. We talked about this how G tends to, or say the reaction free energy, or the free energy has a variation with temperature. If you remember that there was a Gibbs-Helmholtz equation which we discussed some time back, and that basically tells that if we had this thing, dg of t dt, that will be nothing but minus h by it was t square. And similarly, we also wrote it in the differential form, in the sense that if this is correct, then we can say that, okay, fine, what is the value of this quantity? So that will be nothing but minus, we can write it term by term, so d dt of delta G is nothing but G2 minus G1. So suppose the system is undergoing a finite change from state 1 to state 2, divided by t, and now we can actually very cleverly write the Gibbs-Duhem equation in this form. So it is nothing but d dt of G2 by t minus d dt of G1 by t. So according to this definition, again this is the Gibbs-Helmholtz equation, or Gibbs-Helmholtz relation, and then we see that we have minus h2 by RT square minus h1 by RT square, which is nothing but minus h2 minus h1 divided by t square. There won't be any r, which is nothing but minus delta h by t square. Now that exactly what we are going to use. And then what we say here is that we can actually write the Van 't Hoff equation. Now remember that we also could write it in terms of how do you, this is basically the Gibbs-Helmholtz relation, but the question is how do you connect it to the to the equilibrium constant. Now it is very obvious because we have a delta G here. So we'll connect it to the definition of equilibrium constant, and you already know that delta G0 is minus RT ln K, or K equilibrium. So we can write that ln K equilibrium is nothing but minus delta G reaction free energy and the standard state divided by RT. So we can write it, instead of taking the equilibrium constant versus temperature, we can actually write it d ln K equilibrium dt, and then we'll have minus delta G R0, 1 over R you can take common, and basically ddt of this quantity. Now that we are going to use the Van 't Hoff equation, and we already know that it is minus delta H by T square. Now this minus and this minus cancel, so we'll have 1 over RT square, or we can just write it as a delta H by RT square. So alternatively, you could also write the Gibbs-Helmholtz equation in slightly different fashion. Now instead of writing it as like this, you could write it as, say, this 1 over T term. You could actually bring it forward, and then you could write it in terms of d ln K equilibrium d 1 over T, how it varies. Now you can easily figure out what is this quantity. So d of 1 over T is nothing but minus the derivative of the 1 over T, so 1 over T square with a minus sign, and times the differential of T, so that will be dt by with minus 1 over T. So what we could write right from this equation, this particular equation, this is 1 over T square. So that 1 over T square term we are just bringing on the other side. I mean, like this. We can, if we just bring it on the other side, it will be basically multiplied by T square, or you can divide it by 1 over T square and include a minus sign, and then this you will get. So either this equation or this equation, where d ln K dt is del H by RT square, is known as Van 't Hoff equations for a variation of the equilibrium constant with temperature. Now when you have the delta H for the reaction is, say, positive, which means it is an endothermic reaction. Remember that delta H is the heat change associated with the reaction, and heat change positive we say by our convention when the surrounding supplies energy to the system. So these are the endothermic reactions that we discussed. If that is negative, that is positive, then the slope of d ln K dt, basically the slope of ln K versus T curve, will be positive because delta H is positive in this case. Otherwise, if we have an exothermic reaction where heat is released, and then if you plot ln K equilibrium versus temperature, then you will see a negative slope. So then you can actually predict the whether this reaction is endothermic or exothermic by looking at the equilibrium constant, or whether the equilibrium constant is changing with temperature or not. Now what is the essence of that is that well, positive slope means actually we are having when the ln equilibrium, when we are increasing the temperature, if the dt is high, and then we are seeing ln K equilibrium, sorry, or equivalently we can say K equilibrium, that actually is also increasing for endothermic reactions, which means that for endothermic reactions, if we supply heat from outside, how do you change the dt? the dt means actually it's the temperature of the system you are raising, but that you can only do by supplying heat from outside. So if I supply heat from outside, so and increase the temperature, then the K equilibrium of the reaction is also increasing, which means I'll have more product divided by the product versus reactant ratio will be more, which means the forward reaction is getting more and more favored. Because if you remember, whatever is the reaction, whichever way you write it, nu A plus whatever is going to nu B plus whatever reactions, ultimately the equilibrium constant is can be written as the forward versus reverse reaction, which means if that is going higher, this means actually the forward by reverse is getting higher. So the forward is increasing and the reverse is decreasing, or in some way, which means you are getting more product than the reactant. You are shifting the equilibrium towards a new site in a very positive way. This exactly the same opposite thing will happen. So we see that for this case, if I increase it, this ln K equilibrium for an exothermic reaction, or equivalently the equilibrium constant, that decreases for an exothermic reaction, which means if I had reduced the temperature for an exothermic reaction, then I could actually increase the equilibrium constant in the or the product ratio. But usually you might have a kinetic barrier, meaning that the reactants may need a very much initial temperature, some amount of heat in order to form the product. So which means actually they always have a kinetic barrier, in the sense that they need to surmount some amount of energy, or they need to actually spend some amount of energy to cross a barrier, and that crossing of the barrier we will discuss in detail when we discuss the kinetics part. This is known as the activation energy, and that energy has to be supplied first. So it's not always that, don't think that if I go to a 0 Kelvin temperature, then the reaction will be the fastest. It's not like that. So you need a minimum temperature, and then only you can see that, okay, fine, I'll have a maximum amount of the product. So always that's the reason we keep this temperature at an optimal temperature. If you reduce this too much, then actually you cannot get anything. For example, you have studied it like for this famous reaction, which we'll also discuss when we consider the catalysis part, is going to say ammonia, nitrogen and hydrogen, which is extremely important reaction for our survival. Now this reaction is actually exothermic. It produces a lot of heat. So if you have a quencher of heat, or basically if you reduce the temperature, then the reaction will shift towards this side, the forward side, and you'll have more and more ammonia. However, you'll realize that you need some amount of energy in order to proceed this reaction, because the reaction actually involves a step where actually these nitrogen molecules need to be the bond between the nitrogen atoms in the nitrogen molecule needs to be broken to generate this nitrogen atom, which will react with the hydrogen atoms to give you some product. And this reaction happens always in presence of some iron catalyst, and we'll discuss in detail how the surface catalysis works. And then when it happens, then we see that this breakage of the bonds requires some energy. So that is basically the activation barrier of this reaction, because it needs to break the bond and then only it can go to the product side. So that's why Haber, when he did this famous reaction, he kept the temperature, I think, around 550 degrees centigrade, and that he called as the optimal temperature. So you need optimal temperature to be maintained throughout, so that you get the maximum product ratio. It's not like that for every exothermic reaction. You have to, since actually heat is released, you can actually quench the heat. Of course, you can increase the yield, but inherently the system also needs some heat. Otherwise, the reaction will not start at all. So now we'll conclude our part on this chemical equilibrium. So to summarize, what we discussed is that we first discussed the concept of how to write the equilibrium constant. So we showed that the K equilibrium or minus RTLN K equilibrium can be connected to the reaction gives free energy at standard state. Prior to that, we actually defined what is the reaction gives free energy, what is delta H0, how you can write it as a difference between the chemical potentials, and then we kind of expanded it for a general case, and we showed that this delta G reaction free energy can be written as a part which is delta, the standard part, which is actually connected to this K equilibrium, which is nothing but minus RT ln K equilibrium, and plus RT ln Q, where Q is the quotient for at any time. Now Q will be equal to K equilibrium only under equilibrium. And then we basically showed what is the expression for Q or K, and we showed that it is nothing but the summation over all this multiplication over all the terms where the reactants or the products are you take the activity of that particular thing and raise it to the power of the stoichiometric coefficient, but this coefficient will be positive for products and negative for reactants. So that we say what is the stoichiometric coefficient for A, we'll say always minus nu A. We'll never say that it is nu A or that way. So so the negative sign has to be included there. And similarly, if it happens at equilibrium, that means it is equilibrium constant. And then we talked about the effect of external agents, like effect of temperature as well as pressure. Initially we talked about pressure, and then we talked about temperature, and that actually explains how if you want to make a change, the system will always try to counteract the change, which is related to a principle which you studied in high school known as Le Chatelier principle. And we explained why the Le Chatelier principle is like that. We showed you that how if the pressure varies, how the degree of dissociation changes. We also showed you how if the temperature varies, how basically an exothermic or the endothermic reactions are controlled. And this is basically the summary of this part, which we call as equilibrium. And then we'll discuss one application, actually two applications of on thermodynamics or the equilibrium thermodynamics. One is the electrochemistry part, where we talked about what is the electromotive force of a electrochemical cell, a galvanic cell, how basically it generates electricity, and how we can write the electromotive force and connect it to the standard reaction free energy. And the second thing we'll discuss that is on surface chemistry part, or again it's an equilibrium surface chemistry, in the sense that you have a surface and or an interface between two bulk phases, and how you can actually formulate the thermodynamics of the interface, how you can say that whether the molecules will prefer to stay in the bulk phase more or in the interface more. And then we can also classify the molecules based on that particular characteristics. So these two things we'll discuss in the next lecture. Thank you.